Today, we are going to perform a complete metrological calibration of an analytical balance following the strict standards of OIML R76. To begin, you need your reference weights, specifically OIML Class E2 or better. You will also need clean handling tools, like forceps or non-reactive gloves, to protect the weights from contamination. Next, check your environment. The balance must sit on a stable, vibration-free surface. Verify that the ambient temperature and humidity in the room are stable, typically maintaining within 1 degree Celsius per hour. Finally, confirm the balance has been powered on for the manufacturer's recommended warm-up period. For analytical balances, this stabilization phase usually takes between 2 and 4 hours. Skipping these preparation steps introduces invisible errors into the system, primarily thermal drift. This will cause your calibration to fail before you even take your first measurement. Step 1 is recording our baseline. Ensure the weighing pan is empty, close the draft shield, and verify the as-found 0 reading. We then move to the repeatability test. This step determines how consistently the balance measures the exact same mass over multiple cycles under identical conditions. Select a single test weight that is close to the maximum capacity of your balance. Apply the weight, wait for the reading to stabilize, record the exact value, and remove the weight. You must repeat this cycle exactly 10 times. Once you have your 10 recorded values, calculate the standard deviation for the dataset. If the standard deviation is high, it points to underlying mechanical or environmental instability. Even if a reading occasionally hits the correct mass, the instrument cannot be trusted for precision work. Next is the eccentricity test, often called the corner load test. We use this to detect any non-linearity in the load cell when an object is placed off-center. Select a weight approximately 1/3 of maximum capacity. Place the weight exactly in the center and record the reading. Then move it to the front left, back right, and front right, recording the indication at every point. To find your eccentricity error, calculate the maximum difference between your center reading and any of those 4 corner readings. As a firm warning, throughout this process, you must never touch the reference weights with your bare hands. Skipping the corner checks means you will miss mechanical leveling faults, and transferring skin oils onto the weights alters their mass far beyond Class E2 tolerances, immediately invalidating all of your calibration data. Now we run the linearity test. This appraises the balance's accuracy across its entire operational weighing range, rather than at just one isolated capacity. We test at a minimum of 5 specific points: 0, 25%, 50%, 75%, and 100% of the instrument's total capacity. Apply these loads continuously upwards, stacking combinations of weights without returning to 0 between the steps. This chart plots the actual balance readings on the y-axis against the true mass on the x-axis. You must record both the indication and the certified mass value at every step to map out the exact error curve. Verifying linearity proves that the instrument scales its measurements accurately. This ensures a 10-gram sample is measured with the same relative precision as a 100-gram sample. This is the OIML R76-2 test report format. It provides the required structure for documenting all the data you just collected across the performance tests. To evaluate that data, we use the maximum permissible error, or MPE. This is the strict regulatory limit of allowable deviation for your instrument's specific accuracy class. You take the calculated errors from your repeatability, eccentricity, and linearity tests, comparing them directly against these boundaries. The final rule is absolute. Every recorded error must fall safely inside the MPE boundaries to pass. By strictly following this procedure and verifying your data against the MPE limits, you guarantee a fully traceable and legally sound metrological calibration.